Welcome, dynamic students. For this lecture in particle kinematics, we're going to be defining position, velocity, and acceleration in any vector system. And then we're going to be focusing in on what's called rectilinear kinematics, which is 1D straight line motion in either the a hat, j hat, or k hat directions of a Cartesian coordinate system, which will have the very handy side effect of allowing us to kind of look at the whole thing like a scalar because everything's pointed in the same direction. But let's drop back to the basics in more general case. And for that, we'll need to share our notes. So position, velocity, and acceleration. Okay, so we have a path out here in space. So this is effectively 3D. It's moving, in any one of three orthogonal directions. We could define this path, and point P is somewhere on that path, and we can imagine that maybe point P moves along the path according to some time-dependent function. If we can define a reference frame somewhere in space, reference frame with a script F, and we got some point O in that reference frame that defines the origin of the reference system, we can draw a position vector from O to point P, call that a radius vector OP, that will define the position relative to the reference frame, point O, whenever. So we can say, okay, what is the position vector for P? That's one of our important equations of motion. Well, it's ROP. If we're talking about position with respect to that reference frame, which we'll concern ourselves with now. Okay, what's the velocity of point P with respect to reference frame script F? Well, I can define that as simply the time derivative of the position of point P with respect to O, because O is in reference frame F. So great. I will define velocity of point P, which is a vector, as the time derivative of the position of point P. What's the position? Oh, I can define that position as a radius vector pointing from O to P. Okay, great. So I've now defined velocity as the time dependent, the time derivative of position, and I can write it as an ROP. It's a vector, so it has an arrow, and it has a dot, meaning that this is the first time derivative of ROP with respect to t. Okay, how about the acceleration? There's another vector quantity. Well, we know that acceleration is the first time derivative of velocity or the second time derivative of position. Okay, so we'll define acceleration of point P, vector function, as the second time derivative of position, which we've already defined as ROP in this reference frame, which is the same thing as dVP or VP dot. Okay, this applies to however many dimensions. We can define VP and AP in terms of various different coordinate systems. Everything we've said here is general. That's why we define some crazy path out in space. So now we're going to drop into our first kind of simplest subset of kinematics, or study of position, acceleration, velocity with respect to time in a Cartesian coordinate system 1D. So this is rectilinear kinematics, otherwise known as straight line motion in a reference frame. So to sketch this out, we got a reference frame kind of denoted by this blob. It has its reference frame script F, meaning as denoted by the blob. It contains point O, which we're going to use as an origin, and the little hatched line means this is kind of like a starting point. Think of this as like a surface that we would start from, and we've got a line coming out from that surface, and it's pointing in vector direction I hat. If we wanted to flesh this coordinate system out into two other dimensions, we could define a j hat pointing up and a k hat pointing out. But right now we're just keeping it to 1D. We're going to assume all motion that we care about is on this line and is therefore in the I hat direction. So our position of any point of interest, like P, for instance, would be R, OP, just like it was in the general case, but that R now only has a single vector direction, a single vector component, which is the I hat direction. So if we defined the distance along that line in the I hat direction from our reference point O to point P as some x as a function of t, then basically we can define our position ROP, which is going to be a function of time, probably some function of time. It could be constant, but it's a function of time. Is just x of t. So we've kind of taken what is a very vector quantity, which is position, and because there's only one direction we can go, we've kind of turned it into something that we can work with as a scalar. We're either moving forward or we're moving backwards, but we're moving on that line somewhere. So rectilinear kinematics kind of takes a very vector quantity and allows us, once we've defined what the direction is, can't go changing that, with direction in the reference frame, we can treat everything else a bit like a scalar, which we'll see. So just to make sure, we're just going to kind of step through what we're going to do. We're defining position. ROP, just like we did in the general case, is x in the I hat direction. I hat's not going anywhere. It has constant magnitude and direction in the F reference frame. It's invariant in that reference frame. So we can take the time derivative of I hat all day long and get 0. It's great. So we can go ahead and take time derivatives of our position and then take a time derivative of our velocity, just like we defined the definitions of for the general case, and we're going to get something very handy. So we'll start with velocity of point P. This, of course, just a time derivative of ROP, and since ROP is x times I hat, we get the time derivative of x I hat, which is just x dot, or dx dt I hat, because remember, d I hat dt is 0. So x dot I hat, and likewise with acceleration. So the only thing changing is the magnitude. No direction change with time, just magnitude. So if we presume that we are looking in the I hat direction, something we should never take for granted, but we can write a big assumption in our rectilinear kinematics expressions, we really only have to work with scalar magnitudes. That should put us back into a position that we're all hopefully familiar with from physics, where we were doing straight line motion. So rectilinear kinematics is a vector, a subset of the general vector motion, is basically something that we can think of as just having scalar quantities. But let's never forget that we're moving in one vector direction, and that's why we only have to worry about magnitudes. So let's do an example of that. So we're going to look at acceleration of point P in rectilinear motion. Somebody's measured that for us and given it to us. So x double dot dx squared, d squared x dt squared, second time derivative of position, which happens to be our x coordinate, is 5t squared. And something's got a meters per second on it. It should be meters per second squared if the whole expression is acceleration. So I will put a squared on that just to correct the notes. So if t is in seconds, we want the whole expression to be meters per second squared. So the constant phi would have to be probably in meters per second to the fourth. So the overall expression is in meters per second. And we have some initial conditions. Initial velocity, or velocity at time 0, is 2 meters per second, and initial position is -7 meters. So these are initial conditions, as opposed to boundary conditions, which tell you what's going on with some function of interest at a given place. An initial condition gives you information about what's going on with something of interest at a given time, usually time 0. Initial time 0. So we want to know a time-dependent expression for position. So we can just simply integrate a couple of times, invoking our definitions of velocity and acceleration and position and velocity. So we can get a velocity expression from acceleration by integrating. We've got an indefinite integral. So we have a dt, and we get 5/3 t cubed plus a constant of integration. And we can invoke our first initial condition of velocity to solve for c and get c of 2 meters per second. And now we have an entire expression for velocity, 5/3 t cubed plus 2 meters per second equals the velocity whenever. And we can integrate again our entire velocity expression with respect to t, and we kick out a second constant of integration, which we can determine with our second initial condition, which is our position at 0 time as -7 meters equals c2. So we end up with our expression for position, or the magnitude of distance that we've gone from point O to wherever point P is in the I-hat direction at any given time, is given by this function, which should end up in units of meters. So real easy, couple of integrals, inserting our initial conditions to solve for our constants of integration. Okay, so let's mix it up a little. Sometimes we aren't given expressions for acceleration directly in terms of time. Sometimes we're given it in terms of something else, which is itself related to time. So we can invoke our definitions of acceleration and velocity kind of in unique ways. We'll end up using the chain rule to make some handy expressions to mix up our acceleration, velocity, position relationships. So in this case, we're given acceleration of point P in 1D motion, rectilinear. So once again, we're moving only in that I-hat or J-hat or K-hat direction, no other direction. So direction is not changing with time. We're only dealing with the vector magnitudes changing with time. And we're saying in this case, we're told the acceleration x double dot is a function of velocity, and we're given the velocity at time 0, and we're given the position at time 0. So the same initial conditions, and we're asked, hey, can you find the equation for position at any time? It's like, well, great, I can't just integrate velocity with respect to time if I don't know what velocity is as a function of time. But I do know what the definition of velocity is, and the definition of acceleration. So I can use those fundamental definitions to create an integratable expression. So I can say, well, x double dot, or a sub p, the acceleration of p, is another way of just saying the time-dependent change of velocity, right? A equals dv dt, which equals d squared x dt squared. So just write that, okay? Here's dv dt is acceleration. What's acceleration? -2v. Hey, variable separable expression. So I can divide both sides by v, multiply by both sides by dt, and end up with what's effectively a little variable separable differential equation. I can integrate both sides with respect to the differential expressions. So I'm going to integrate the left-hand side with respect to velocity, and I'm going to integrate, the right-hand side with respect to time, and I'm going to end up with the natural log of velocity being equal to -2t plus some constant, and I can then take the exponent of both sides to get an independent expression for velocity, and my constant of integration just rides along. And I can use my initial condition, velocity at time 0 equals 2, to determine what that constant is. Ends up being natural log of 2. And so I can throw it up in there. I could use properties of exponents to basically bring that down as a constant multiplier if I wanted to, but I'm just going to leave it up there. It doesn't really matter. But if I wanted an expression for position, I have velocity, which is the first time derivative of position. So all I have to do is integrate again with respect to time of this term to get x at any time. So I will do that. Integral dx equals the integral of my exponent function with respect to t. So let's not forget what we're integrating with respect to. That becomes really important here. So I end up with position x at any time is going to be basically the integral of this expression. And so here's the integrated expression. And of course we kick out another constant of integration. There's no limits on our integral, so we're just going to have constants of integration. So we're told that x is -7 when t is 0. So if I put a t of 0 in, I will get exponent of natural log of 2, which is 2, times -1/2 is -1. So to get x of 0 at -6, C2 has to be, or -7, C2 has to be -6. So I can plop that in for C2 and get a full specific particular solution for position at any time. So again, very similar to what we did in the first example, except we had to use a little bit of mathematical manipulation of the basic definition of acceleration as dv dt to crank through the math, because we needed an expression of velocity with respect to time to integrate. So let's look at another variation on that. This time we've got what looks like those same initial conditions, and someone has given us an acceleration that is position dependent. So our acceleration depends on position. So looking ahead, giving a glimpse ahead into kinetics, this would very likely result in a position dependent resultant force, of which we can probably think of a bunch of those, like different vector fields that might be proportional to how far away you are. That's pretty common. We can think of a lot of things that might produce a position dependent acceleration due to a resultant force changing with position. So this is the one we got for this particular problem. So now we're back to effectively saying, well, how do I set this up to integrate again? So we're going to use another definitional mathematical trick that is based on the definitions again of just acceleration, velocity, position with respect to time. So acceleration is the given function of x, which is the same as saying the first time derivative of velocity. And we know that acceleration equals dv dt. And we know that velocity equals dx dt, provided the direction's not changing, that we're in our rectilinear system. So what we're going to do is we're going to take this expression here, a equals dv dt, and we're going to multiply both sides by velocity. Except in the case of the left-hand side, we're going to express velocity this way. And on the right-hand side, we're going to express velocity this way. But, we've just multiplied by velocity on both sides. So we haven't, it's still a valid equation. So we took this expression and we multiplied the right and left-hand sides by velocity, except we used a different appearance of the velocity expression for each one. So now we have something that's a little bit easier to manipulate from the standpoint of integration. So we basically can just take this entire expression and look at it from the standpoint of the differentials dv and dx. So effectively we have a dx equals v dv. The fact that x and v are both varying with time is irrelevant. We can still write, our acceleration, a bit of acceleration with any bit of x is equal to the velocity times any bit of velocity change. So we can integrate both of those expressions here, and now we have something that we can actually integrate. So we know a is a function of x, so now we can integrate a function of x with respect to x, and v is definitely a function of v, so we can integrate v dv, and so we get our integral with respect to x on the left-hand side and our integral with respect to v on the right-hand side. We would technically kick out a constant of integration on both sides, but we'll combine those two constants into one constant c1, and then we'll use our initial condition to solve for that. We'll rearrange to get velocity in terms of position, and use our initial condition of velocity and position at any given time. So v equals 2 milliseconds when x equals -7 meters, which is when t equals 0. So we're invoking both initial conditions to get C1. So we get C1 equals 100 when we use some algebra there. So now we have a full expression of velocity at any position-dependent velocity. Okay. So we can now, we know velocity is just dx dt, and so we can again just move all of the x-dependent terms over to the dx side and vice versa with time, and now we can again integrate each side with respect to its respective d whatever variable. So we can integrate each side and end up having to, we have to use some trigonometric identities, a trig ID, to integrate this term, and that's something you can look up in a table of integrals at this point. Definitely won't ask you to derive this unless you want to. You're always welcome to, but this is definitely something that can either be looked up, or if you are doing any kind of form of numerical integration, you could definitely use trapezoidal rule or Simpson's rule or one of the many numerical integration rules to solve this. You won't need to over on this side. That'll just be 2t plus a constant. But regardless, using an integral table, I found that the integral with respect to x of 50 minus x squared all to the -1/2 was inverse sine of x over square root of 50. And of course that equaled the integral of the other side. Now I can use my initial conditions again and say x equals -7 when t equals 0 and solve for C2. And now I can just put that back in here and write an expression for x by simply taking the sine of both sides and then multiplying by square root of 50. So 3 examples of rectilinear motion where direction is not changing with time. So all we have to be concerned with is the time-dependent relationships between acceleration, velocity, and position, and any combination thereof. And we know that we can use the definitions of acceleration in terms of velocity, velocity in terms of position, since all 3 are time dependent, to express them in terms of each other and do some creative mathematics like up here, so that we can get things into an integratable form based on whatever functions we happen to know. So that's just a little mathematics. I'm going to end this recording at this point, but just looking at a glimpse of our next topic. We're going to take everything we know about rectilinear motion, where direction is not changing, and we're going to continue to leverage relationships between acceleration, position, and velocity, and we're going to start throwing in the ideas of relative reference frames in terms of knowing one thing and relating rates to it. So if any of you studied in calculus or physics a topic called related rates, we're going to be revisiting that in the next lecture, in the next couple of examples, just to get us used to thinking in terms of basic related rates, and as kind of a way of thinking about relative reference frames.